And give me one moment. I will do a backup recording.
Okay, don't worry about that.
Okay, I record another one locally. I don't know if it works, but just in case. Okay, okay, we're recording. Okay, so yeah, good afternoon, everyone, and welcome to the Physics Department of Xiamen University, Malaysia. My name is Yan Keng, and I'm here to introduce you our speaker for today, Dr. Feng Siyi. So Dr. Feng is currently an associate professor in the Department of Astronomy at Xiamen University. She received her Ph.D. degree in Physics and Astronomy from the Ruprecht Karl University of Heidelberg and Max-Planck-Institute of Astronomy in 2015, and worked as an independent postdoc fellow at the Max-Planck-Institute for Extraterrestrial Physics from 2015 to 2017, and East Asian Core Observatories Association from 2017 to 2021. Her research interests are the molecular complexity in the interstellar medium and the origin of life. Dr. Feng is an expert in submillimeter interferometry and astrochemistry. She has more than 700 hours of observational data as a principal investigator with more than 80% successful proposing rate and more than 1,300 hours observational data as co-investigator. Using the world's leading interferometers like JVLA, ALMA, SMA, and NOEMA, and single dish telescopes. She is currently leading an international team for several multi-wavelength line image survey projects. These observation projects are in the aim of characterizing the dynamo-chemical properties of the star and planetary forming systems, and at a spatial scale of 20 parsecs down to 50 astronomical units throughout the galaxy. So she's here today to talk about traveling through time and space. And without further ado, let me pass it over to Dr. Feng.
Thank you. Thank you, Dr. Lim, for this nice introduction. I didn't expect that you introduced all of this and I put too much. So thank you for giving me this opportunity to give this public talk. Well, actually, in the very beginning of this semester, when I got this invitation of giving the talk, I thought it is a challenge because I was working on some specific small fields in astronomy. Astronomy is a kind of large topic. It includes everything. Later, I will mention about that. So I was teaching for this Astronomy 101 course in this Malaysia campus this semester. That bring me a lot of opportunity to refresh my memory and refresh my knowledge. And this public talk is for anybody who is curious about astronomy. Since what the information I got is majority of the audience are high school and undergraduate students who are interested in this natural science. I will try to use a public outreach language and give you a brief introduction on these three topics. What are the big questions in astronomy? What do the astronomers do? What tools do astronomers use? And what kind of astronomy education and research can Xiamen University offer you? Of course, all of these are based on my own understanding, and some of them might be acceptably subjective. So please be a critical thinker during my presentation, and I would be happy to take any questions afterwards. Okay, so I can start. You may ask me, what is astronomy? Well, ever since the first step out of the proverbial cave, humans never stopped their appreciation to the beauty of the night sky. They never stopped their curiosity about the infinite possibility of the time and the space. Where did we come from? Are we alone in the universe? What is the beginning and the fate of the universe? So using the scientific methods, we're trying to answer this question, part of these questions, and that is astronomy. Astronomy is a science that is the closest science from our everyday experience, studying the most distant objects. And it is the oldest science, exploring the youngest universe. Taking advantage of the development of the modern telescope, this field is progressing at a breathtaking pace, with discoveries being announced almost every day. In other words, it is our curiosity to the nature that triggers the innovation of the modern technology. And this technology, such as the invention of CCD, the radio communication, and so on, they changes our life. In astronomy, we study the universe, but what is the universe? Here I have to cite an ancient Chinese phrase about the definition of the universe. Literally translation, that is, the universe is about the time and the space. It covers the time scale ranges from the beginning to the present till the end. And it covers the space scale, including all the dimensions. So doing astronomy research is studying the universe. That means we're traveling through the time and the space. Here I'm showing you the space-time diagram. That is a graphic way astronomers describe the size of the universe. By convention, the space is plotted horizontally and the time is plotted vertically, increasing upward. If you think space-time diagram is difficult to understand, please just imagine you are setting appointment with your friends about this dinner. You are setting this appointment to mention about the place and the time. If your friends miss the place and miss the proper time, you guys cannot meet each other. And afterwards, for the high school students and also for the undergraduate students, once you learn something about the general relativity, you will know that when we talk about the space and the time in the universe, we're talking about the same thing. And that is Einstein's space-time continuum. And the essential reason is gravity. Gravity links the space and the time, and this has been proved by many evidences, including the detection of the gravitational wave. Those are generated by the accelerated masses and propagate as waves outwards from their source at the speed of the light. And the universe is made of matter and energy. Protons, neutrons, electrons, neutrinos, planets, stars, galaxies, all forms of matter and energy are in the space and the time. So not only the night, but also all the electromagnetic wave, from radio wave, infrared, visible, UV, X-ray, gamma ray, and so on, they are disturbance in the curvature of the space and time. Therefore, it took them a long time to reach us from the distant object. And what we see those objects now are what they were at a very young age. So looking out in space means you're looking back in time. Okay. The infinite speed of the night bring us some limitations in understanding the universe. Like when the universe starts, will there be an end? How large is large? And how small is small? Those are some big questions in astronomy. And the first one is, where did we come from? Where did the life, our planet, and the entire universe come from? That is the most fundamental question of humanity. So many cultures, including the Chinese Pangu, and the Buddhism and the Hindu Brahman, the Christian Jesus, they are all their own creators. Ancient people place the creation story in a cycle so that they can explain the disappear and the appear of the matter and the energy. A modern theory of the origin of the universe starts with the idea of the expanding space. In 1929, this Belgian Catholic priest, and he's also a mathematician, Georges Lemaitre, I'm not sure if I pronounced his name correctly, but please just correct me if I was wrong. And he firstly hypothesized a revolutionary idea. At one time, the universe might have been as small as an atomic nucleus, and that is called a cosmic singularity. When the universe was infinitely small and infinitely curved, all matter and energy were concentrated in a single point. In the beginning, many astrophysics found the idea is bizarre and distasteful, Those who dislike this idea gave the name as Big Bang. The scientific story of creation in the Big Bang model works like this. The beginning was a time when the energy and the density was so high that the mass and the energy were freely interchangeable. So the mass can change to the energy and the energy can change to the mass. Then it expands. As a result of the inflation, the universe became flat, smooth, and virtually empty. The expanding universe was filled with primarily radiation along with the residue of the matter. So over the next 3 minutes, while the entire universe was still hotter than the center of the star, a quarter of the mass of the universe was fused from the hydrogen into helium. As the universe expanded and cooled, radiation thinned out more rapidly than the matter. Until 10,000 years, the universe became matter-dominated. After 380,000 years, the universe became transparent. As the electrons were able to join atomic nuclei to form the stable atoms, today, billions of years later, the radiation from this era has been diluted and redshifted to the microwaves. And that is the cosmic background's microwave radiation. So gradually, the gravity sculpted the entire early universe into the structure on no scales. This process was influenced by the large amount of unseen dark matter. About 500 million years after the Big Bang, enormous gas clouds collapsed into the first galaxy. Within them, stars switched on for the first time, and the stars followed a pattern of the birth and the death for 6 to 7 billion years. Most stars die in a quiet death, fading slowly. The massive stars, they explode, filling the space between the stars with heavy elements. And many stars end up surrounded by the debris of their own creations. On one such rocky fragment, the life evolved out as a watery organic broth. 4.5 billion years later, they warmed by the yellow star and bathed in the microwave afterglow of the creation event. And humans point their telescopes at the skies and ponder the meaning of it all. This is a Big Bang model. And the Big Bang model brings us a picture like this. Our observations of the nearby galaxies, they represent a single frame in a movie. And that has been playing for billions of years. If we wind the tape backwards, we can see snapshots of galaxies at progressively larger distance. They move closer together. That is a progressively older universe. Observationally, we cannot see all the way back to the first moments, but we can see times when galaxies were first forming and the large structures that we called the cosmic walls and voids. They were just starting to form in a smaller, actually a tiny universe. And when we keep on looking back, the volume of the universe contracts until all the mass is smashed together. The mass that formed the galaxies and the stars break down into the hot gas, and the universe turns towards the state of the infinite temperature and the density. So the initial singularity of the Big Bang, that is what I'm currently pointing at, that contains all space and the matter, and that is to say, time itself begins with the Big Bang. This Big Bang had no center, no past. It simply was a sudden beginning of everything in an expanding geometry that may or may not be finite. We don't know. So to many people, astronomy's description of the Big Bang is more fantastic than any creation myth. As a critical thinker, it's important to evaluate this scientific creation story. And you may ask me, how secure is the Big Bang model? And are there any other ways of explaining the universe we live, which match the observation data better? Well, currently, we have 3 pillars of the evidence for the Big Bang. The expansion traced by the recession of the galaxies, that is a famous Hubble's law. And the cosmic background radiation, that is a relic from the Big Bang, to the microwave band, and the abundance of the helium that is created by the cosmic nuclear synthesis. However, this theory is not a flawless theory. There are still a lot of questions. What is the physics a microsecond after the Big Bang? When the matter in the universe came into existence? When the asymmetry between the matter and the antimatter originated? And the ultimate question is, what caused the Big Bang? And what, if anything, came before the Big Bang? Okay, that's a Big Bang. Actually, in purpose of the scientific education and the popular science, this famous American astrobiologist, Carl Sagan, he popularized this concept of the cosmic calendar in his 1977 book, and also in his famous 1980 television series, Cosmos. It is a method to visualize the chronology of the universe, and that is scaling its currently understood age of 13.8 billion years to a single year. In this visualization, 437.5 years are scaled to each second, and 1.5 million years are scaled to an hour, and 37.8 million years is scaled to 1 day. So the Big Bang took place at the beginning of January the 1st at midnight. Here I'm pointing at. And the first galaxies were formed on January the 22nd. The Milky Way galaxy was formed on March the 11th. And the formation of the solar system happens on September the 2nd. The oldest rocks known on Earth was formed on September the 6th. And the evolution of the life on Earth starts from September the 14th. It is only on December the 30th that the dinosaurs die out, and the primates, apes, and the hominids, they evolve. On December the 31st, the last day, especially the last 30 seconds, the last ice age is ended, and the history begins. And the modern history started from the last second of December the 31, and that lasts only 437.5 years before the present. So from the Planck scale to the cosmic horizon, the visible universe encompasses about 60 orders of magnitude. The size scales of the universe can be arrayed around the serpent-like minutes, around the face of a clock. Sheldon Glasgow, this Nobel Prize-winning American theoretical physicist, originally suggested this symbol as a serpent, and he's a man holding his sketch about the standard model. So this cosmic Eurobonds, with the swallowing of the tail, expressing his hope for unification of the theories which govern the largest and the smallest structures. The cosmic Eurobonds represent the universe as a continuity of vastly different size scale. The diameter of the Earth is about 2 orders of magnitude smaller than that of the Sun. That is what I'm pointing at. And about 60 orders of magnitude, they separate the very smallest from the very largest size. Traveling clockwise around the serpent from the tail to the head, we move from the maximum scale we can see, that is the size of the cosmic horizon, down to that of a supercluster of the galaxies, down to a single galaxy, to the distance from the Earth to the great nebula in Orion, to the solar system, to the sun, the Earth, a mountain, a human, and an ant. A single-celled creature, such as a bacteria, a strand of the DNA, and an atom, and a nucleus. The scale of the weak interaction carried by the W and the Z particles, and approaching the tail, that is the extremely small size scales on which physicists hope to find massive dark matter particles. And on even smaller scale, a grand unified theory, GUT, The tip of the tail represents smallest possible scale, the Planck length. In the circle, the human beings are just about at the center. Then, the universe, that is hierarchic. A cosmologic model originally proposed by the Swiss-Tisch astronomer Karl in 1908. That is, inhomogeneity exists on increasingly large scales. The galaxies occur in clusters, which in turn are clusters into superclusters, which may in turn aggregate as clusters of superclusters, and so on. As the level of the clustering increases, the mean density of the matter must decrease in a progressively larger volume. So this is our cosmic address: the Earth, the solar system, the Oort cloud, the local fluffy, the local bubble, the Orion arm, the Milky Way galaxy, the local group, and the Virgo supercluster, and the Naniakic supercluster, and the observable universe. So our universe expanding since there's no center. When we look towards any direction, we see out in space and back in time. As time goes by, larger and larger regions of the universe become visible to us. We say that the observable universe, here I'm using a red circle, and that is grows a little larger every day. The steadily growing boundary of the observable universe is our horizon. We say the more distant objects reaches our telescope as they enter our horizon. So please be aware that the earliest expansion was faster than the speed of the light. So there are regions of the space we have never seen. And the observable universe is distinct from the physical open universe. The observable universe is limited to the regions from which light has had a time to reach us. But an open universe is infinite in size, and the dark energy is part of the universe we cannot see. To give you an impression on the size we study in astronomy, here I'm showing you a video which is about 3 minutes. I think the students who are taking my course, they've already watched this video, but let's just share how vast the 60 magnitude are there in our universe. Okay, so that is a scale range, how vast that is for 16 magnitude difference. And scientifically and spiritually, I bet every of us ask our parents this question: what are we? Where are we from? Why are we here? Human beings have asked all these questions throughout the entire history, the human history. The universe is filled with a gas and a small part of the dust. How do the star dust make up the atoms, molecules, proteins, DNA, RNA, and us? That is one of the frontier astronomic fields, astrochemistry. Astrochemists like me, we want to understand the formation, destruction, excitation of the molecules in an extreme astronomic environment and their influence on the structure, dynamics, and evolution of the astronomic objects. That is a big goal. To achieve this goal, we need generations of the cross-field collaborations. Taking the searching for the complexity of the organics as example, first, to understand where they might be in the universe, we need astrophysicists and the chemists. According to the geochemists, there are more than 200 amino acids identified in the meteorites. With the help of the biologists, 20 of them are the building blocks of the life. After analyzing abundance and the spatial distributions of the molecules from the extraterrestrial environment, we compare the thermodynamic properties of the different molecules with those from the ground-based spectroscopy and the chemical labs. We will try to understand when, how, and where are the molecules formed, excited, and stored in the interstellar medium. How are they cycled through the formation, evolution, and the death of the star and the planetary system? And how far can the chemical complexity go? How universal are the building blocks of the life? Besides the confronted with the mystery of our own existence by asking, how did life begin? We also have some other questions. Is life ubiquitous or unique? Are we alone in the universe? Where are they? Questions like this are central to the new scientific field that's called astrobiology. Finding an answer to this question will require the work of more than just one group of scientists. For instance, to understand how the origin, evolution, and the future of the life on the Earth and the universe, we need to study our home site, the Earth, at first, and tell what is the geologic conditions, the type of the chemistry, the rate of the asteroids impact were likely to occur, and what are the steps leading from chemistry to biology on early Earth. Scientists with backgrounds of geology, biology, astronomy, chemistry, physics, philosophy, religion, and mathematics, they're learning to collaborate in their common endeavor. We live in a universe that is enormously large and cold, in which we are insignificant players. Most of the astrobiologists would agree that the basic ingredients of life are not uncommon in the universe. As a matter of fact, we can be found almost everywhere. Organic molecules, including the planets, are the products of the star. Up till now, over 3,500 planets have now been identified beyond our solar system, and they are being discovered at a rate of about several hundred every year. A number of these are the Earth-like planets in the habitable zones of the Sun-like stars. Furthermore, there are several places within our solar system where we may yet find microbial life, or at least a trace of its past existence. For those planets where energy, liquid water, and the right chemicals are not simultaneously present, we classify them as inhabitable currently. But is it only a matter of the time? We think that the hydrogen, oxygen, carbon, and the nitrogen are all elements necessary for the life. However, why scientists have not been able to reproduce the progress from organic molecules to the simple life in the laboratory life? As a matter of fact, how to define the life, the intelligence, that is tough. And cruel and obvious truth is, we can only observe a universe that is capable of allowing us to exist. Our predictions about the possibilities for the life is based on a single data point, and that data point is a life on Earth. Is heavy elements and long-lived stars absolutely requirement for the life? We don't know. If there is a kind of extraterrestrial life forms in the universe rather than us, where are they? After ages of trying, we don't even know how to contact with them. Why we still have no evidence for the aliens who have made a visit to our planet or otherwise try to establish contact with us. Is that because the development of life in the universe is not a commonplace and we are indeed alone? Or the closest intelligent civilization is just too far away? Or is it a natural progress that the civilization is determined to destroy itself before successfully navigating to the universe? Or we are the only civilization who finds morality in communication across the space? Or aliens never resemble us physically or culturally? So it is like a story about setting a dinner appointment with your friends, as I mentioned in the very first beginning. But the problem we came with is we don't know where shall we meet, when we can meet, and who we will meet. So it's just like we're sending the message in a bottle towards a vast space and the time. So what does the future hold for our universe? That is a main concern of cosmology. Theoretic restrictions predict several possible scenarios for the evolution and the ultimate fate of the universe. The problem is how to use the observations to test them. The Big Bang theory, supported by the rate of the expansion, average density of the matter, and the physical properties of the mass energy in the universe. Those three pillars I've already showed you. They indicate that the universe is expanding. Whether that expansion will continue, accelerate, or reverse, factors such as the average motions of the galaxies, the shape and the structure of the universe, and the amount of the dark matter and dark energy that the universe contains, they have to be concerned. So I was supposed to show this movie about the journey through the simulated universe in three-dimensional, and that is called the Millennium Simulation. I bet most of you have already seen that. And it is used more than 10 billion of the particles to trace the evolution of the matter distribution in a cube region of the universe. On the way, we visit a rich cluster of the galaxies and fly around it. So the entire video is about 2 minutes, and we travel at a distance for which light would need more than 2.4 billion years. Because of the time, here I'm going to show only probably 5 seconds, just to enjoy the music a little bit. Okay, so if you're interested, please just check it with the Max-Planck-Institute, the Millennium Simulation by yourself. And it's magnificent, and it took them a lot of energy and the computer resources to produce such kind of simulation in 3 dimensions. So if the universe holds enough matter, including the dark matter, will the combined gravitational attraction of everything will gradually halt this expansion and lead to the ultimate collapse? What if the dark energy, the strength of which appears to be independent of the space and time, the dark accelerates the expansion even more than is expected? Will the universe, like an exploded balloon, that's every system, the galactic clusters, the solar system, that will disintegrate? The stars, the atoms, they'll finally be ripped apart, leaving behind nothing but decay into energy. Will the universe finally turn to be an isolated island with low potential to receive light from each other, and then become nothing more than a smooth, cold distribution of energy? We don't know, and we're still asking for these questions, and that is a cosmology. So, of all those big questions, I only list 3 of them, and there are, of course, a lot of. And of all of them, astronomers, they're working to find some evidence to these questions, generations by generations, team by team. Probably we'll never know that until the end of the universe, but that's a kind of thing. And you might be curious, what do the astronomers really do during their daily life? So my friend think I was staring at the sky all the night, catching the shooting star, predicting the aurora, solar eclipse, and doing something like photographing. So some of them even asked me to tell them whether their constellation will be blessed or misfortunate tomorrow or the next week. I don't know. My mom think I was working hard on the lab course all the day. Well, that is part of the truth. I was sitting in front of my computer, especially when I was a student, observing, programming, reducing the data, and writing scientific paper. Why I do this? Well, the fact is, the picture you saw from the journals, maxims, postcards, or TV show, they are not directly from the telescope. We use binary data. And megabytes, gigabytes, terabytes, or PB of the binary data to store and transfer all the information. What we are doing is converting this binary data into those beautiful pictures and search for the physics behind them. And that is basically what I was doing during my undergraduate to the postdoc life. So what can we do after we graduate? There are a lot of possibilities. Of course, the first option is being an astronomer. So if you take it as a career, the best routine is to be a professor or a research scientist. We have to admit that this is a kind of tough road, and you will come with a lot of difficulties. And you will need more patience than your friends who study economy or engineer. Only if you have the determine to do it, please do it. Please go ahead. But think carefully. Just take my personal experience, for example. I'm not sure if I'm a stereotype or not. I got my PhD degree in 2015. That was 22 years since I started my elementary school, and become a faculty member in Xiamen University after 5 years of the postdoc experience. So if you're going to be an observer like me, here I'm blinking, that is a control room of one of my observation in Japan, Nobiyama Observatory. In the wintertime, you can see a lot of snow outside of the window. It is beautiful, but sometimes it is a little lonely. That means being an observer, you will have to be through hundreds of slides, presenting observational proposal, time and times of compete with the other observers in the world so that you can get the telescope time. So if you start your observation, congratulations, that's half of the way, but that is not the end of the story. In rare cases, you got exciting results. Most of the time, the weathers are not ideal. Like this time, there are a lot of snow, so we cannot run the observation for the radio telescope. Or sometimes you got nothing. And if you got the data as being blessed by probably the God or the constellation of yourself, I don't know, then you will spend a month in running the data reduction progress with your own computer or the computer cluster, do the data analysis, writing paper, and arguing with the referee, and doing presentation to let anybody else know your work. Of course, to keep up with the others in your field, reading others' paper is a daily routine. See, there are a lot of training during this progress, and after you got a PhD degree, you will be an independent researcher, and you will lead your own team to think about some big questions, as I mentioned. And the good side is, if you don't want to pursue an academic life, there are some other options. benefit from the training process you've got as an astronomy major. You will have the skill of thinking with the scientific methods, writing skill, data analysis skill, programming skill, and the most important is the communication skill. So let's see from this list I'm showing you, what are some of my fellow classmates are currently doing. Actually, I asked them one by one. They can be a data scientist. They can be the planetarium director, as here I'm showing you, that is a planetarium in Shanghai and Dishui Lake. And they can go to the patent office like Einstein did. And they can be a double E engineer. And they can be the computer grammar, science teacher, business analyst, science journalist, technical writer, and sales manager, and the photographer. A lot of possibilities. And probably when you hear my daily life since I was a PhD student, you will be frightened and ask me, why you still feel happy of suffering of this? No, it's not suffering. Please don't get me wrong. When I was reading some forum, a lot of people, I don't know why, they always frighten those young students who has no astronomy backgrounds about how difficult this field is, about how good the mathematics and physics skill you need. It's true that we need those skills, but the most important is your curiosity and your passion. The reason that I would like to be an astronomer is my curiosity to the nature. And also, as a benefit for each of my observations, I got the chance in those most beautiful and the cool places. Observatories are all built in the dark, high, and the dry places. Once my observation proposal is approved, I got the chance to touch the clear sky and to ski or to dive. And also there are some other astronomers, for example, the theorists. Here I'm showing you well, I cannot find my mouse, but the upper level, the upper panel, that is one of my classmates, and he's currently a Hubble Fellow in MIT. And the lower panel here, that is Professor Hao Ranyu. He's also an associate professor in Xiamen University of the main campus. They're all theorists, but they're not staring at the blackboard, doing calculation and make predictions all the day. They're running simulations. Of course, that takes a long time. So running the codes, it takes like days or the months, like the Millennium simulation I just showed you. During this time, they don't wait, they just go outside for cycling. And after they return from their cycling trip, they can check their code and the results. And there are some other astronomers who are instrument engineers, like this one, who are smiling with his big, brightened teeth. And he's an engineer. Well, the engineers, they're not dealing with a screwdriver all the day or making mirror all the day. They have their personal life. Actually, in order to deal with the maintenance of the telescope, they sometimes investigate the telescope site. So you can see their social network. They're climbing the beautiful mountains or most daily. And then what tools do the astronomers use? Well, in the previous slide, I mentioned the academic and the personal life. In principle, if you are an astronomer, you have your specialty in one side. Either you are a theorist, and a modeler, observer, or instrument engineer. One friend of mine, who is currently a research scientist in Shanghai Observatory, he made this funny table like 10 years ago when we started our PhD. Of course, this is for fun, and it's a stereotype for the different classification of the astronomers. Once you're doing research, there's no distinction. There are a lot of astronomers who do both observation and theoretical modeling, or astronomers who do both observation and instrument developing, or they do them all. Well, astronomy is a kind of science. There are three keys of science: the terminology, that is a precisely definition; the measurements, that is a quantitative and repeatable; and the assertion, that are backed up by evidence. Well, there are several essential steps in the scientific method, and that applies to astronomy. The first step is gathering the evidence. In some scientific fields like chemistry, physics, and biology, evidence often comes from the experiments or from the lab. In astronomy, usually the evidence might be physical, like the rock spot back from the moon, or it might be data, like measurements of the electromagnetic radiation by a telescope. Well, the statements made no evidence to support them are called speculation. Without supporting evidence, there is no way to prove or disprove them. The second essential step is to analyze the data. This usually involves a process of pattern recognition. For example, the astronomers, they might analyze the motion of the planets in the sky at night and to recognize their regularity in the motion. Or they might find a similarity in the chemical composition of the stars in different parts of our galaxy. However, searching for the patterns in data and judge what is the nature is so complicated because the observations, they are a lot limited in number and they have errors or uncertainties. So the third step is explanation for the results of the analysis, and that is called the hypothesis. Sometimes we call them as a working hypothesis to emphasize only the tentative proposal. Please keep in mind, there are always more than several possibilities for the explanation for any set of the data. And that is the reason why most astronomers have strong personality, or sometimes they are a little bit aggressive and they argue so much. And the last step is a critical evaluation of the hypothesis through testing. Of all the hypotheses scientific proposed, the wrong ones are weeded out by such kind of test, and they search for a new one. With hypothesis that has been tested repeatedly, survive, and cover the broad scope of the phenomenon and the application, they're accepted widely as a theory. So that comes with a theory. And the Big Bang is a kind of theory nowadays. Okay. For the observers, our tools are the telescopes. The night sky has always served as a source of wonder and a mystery to the people. However, our universe contains the objects that produced a vast range of the radiation with wavelength either too short or too long for our eyes. The goal for the telescope in every wavelength is to collect as much light as possible and focus a sharp, detailed image on a detector. Different wavelength of the radiation has different transmission window on the Earth. Because of the absorption of the scattering by the gas and the dust in the atmosphere, the ground-based telescope, here I'm blinking, has a very narrow window for the radio and part of the infrared waves. So we launch the telescopes towards the space. It's only from the second half of the 20th century, as rockets and the satellites technology improved, the space observatories were built, which carried and narrated tools to capture the images and the spectrum at a variety of the wavelengths. Communication systems were developed to share the images and the data from land and space-based telescopes. That allows astronomers to get a more complete picture of the universe. Also, using the new technology, astronomers are hoping to detect not only the full spectrum of the electromagnetic waves, but also the nature's message from the space, and they reach the Earth in other forms. For example, the cosmic rays are high-energy charged particles. They are produced in distant part of the galaxy, and they are traveling at a very close to the speed of the light. One way of catching the cosmic ray is using different detectors to observe aspect of the cosmic ray air shower. Astronomers place an underground nuclear reactor like the Pierre Auger Observatory, or like the Large High Altitude Air Shower Observatory that is placed at the western part of China near Tibet, about more than 4,000 meters altitude. and they catch the air showers triggered by gamma rays and the cosmic rays. Astronomers have also begun trying to detect a tiny, ghostly particle that is called neutrino. These tiny particles are produced in the cores of the star, in active galaxies, and as relic from the early universe. Using the vast tanks of fluid as detectors, building underground, astronomers hope to catch the light flash from the very occasional neutrino interaction with atomic particles in the fluid, like this one I'm blinking, the super Kamiokande, and also the ice cube in the South Pole. Well, perhaps the most exotic signal from the space is a gravitational wave. According to the Einstein's general relativity, they are formed rapidly in motion and changes in the state of matter, and they travel at the speed of the light. They're like the ripples in the structure of the space. So we use the advanced laser interferometer gravitational wave observatory, the LIGO, to reach the necessary sensitivity for its detection. Or place it into the space, like flying along an Earth-like heliocentric orbit, well, that is surrounding the sun with 3 antennas, like this one, Lisa. And also as the Chinese Taiji program. And we also place these triangular antennas in the space orbiting the Earth, like the Chinese Tianqin program. Okay. The telescope on the spacecraft provides us a wealth of information about the planet, but there's no better way of exploring the planet than within the planet atmosphere or on its solid ground. A flyby, that is a space flight passing approximately to another astronomic body. Important parameters are the time and the distance of the closest approach. So that is a travel about the space and the time. The Voyager program is an ongoing American scientific program that employs 2 robotic interstellar probes, Voyager number 1 and number 2. Both of them were launched in 1977. The goal is to fly near the planets while collecting data for transmission back to the Earth. Number 1 is for Jupiter and Saturn, and number 2 is for Uranus and the Neptune. In 2019, scientists received a message from Voyager number 2. Well, that was a message this spacecraft sent 1 year ago. They just delivered to the Earth. And they reported that it officially reached the interstellar medium. That is a region of the outer space beyond the influence of the solar wind. For the record, Voyager number 1 had reached the interstellar medium earlier in 2012, about 7 years earlier. As of this year, both Voyager are still in operation, continue to collect and transmit useful data to the Earth. They did things no one predicted, found scenarios no one expected, and promised to outlive its inventors. There are also some other flybys and orbiters like Juno, that is a NASA space probe orbiting planet around the Jupiter. It is powered by the solar panels, and the Cassini-Huygens space mission involved a collaboration among NASA, European Space Agency, and the Italian Space Agency to send the space probe to study the Saturn and its system, including the ring and the natural satellites. And then the Kepler, that is a telescope launched by NASA in 2009. Its discovery Earth-sized planets orbiting the other stars, and it retires in 2018. With its successor, the transiting exoplanet survey satellite TESS, that is searching for the exoplanets in 400 times larger area than Kepler mission. As of April this year, TESS has identified more than 2,600 candidate exoplanets, of which more than 100, well, when I check, it's about 120 something, haven't been confirmed so far. Well, spacecraft have landed on the Moon, the Mars, the Venus, Saturn's largest moon, Titan, several asteroids, and a comet. These spacecraft have planetary surface exploration device and call them as rover. Move across the solid surface on a planet or other planetary mass celestial bodies. They took pictures, measured the surface chemistry, and conducted experiments to determine the physical properties of the surface rock and the soils. The Apollo program that is carried by the NASA from 1968 to 1972. In particular, Apollo 11 succeeded in preparing and landing the first humans on the moon in 1969. The Chinese lunar exploration program, also known as the Chang'e, that is a goddess of the moon in Chinese myth, the Chang'e project, that is an ongoing series of the robotic moon mission by the China National Space Administration. In particular, Chang'e number 5, which launched on November the 23rd the last year and returned about 20-something days later in the same year. They brought more than 1 kilogram of the lunar samples back to the Earth. Well, another interplanetary mission by the Chinese National Space Administration is Tianwen number 1, and the mission was launched July the last year and touched down on Mars after 10 months, and a rover called Zhurong that is now exploring the Martian surface. Of course, the instrument development is growing so fast in China nowadays. Besides the operation of the modern telescopes at a multi-wavelength, here I'm blinking, like the LAMOST, the Dark Matter Explorer Wukong, the 500-meter aperture spherical radio telescope, 中国天眼, and also the Tiangong number 2, the hard X-ray modulation telescope, 慧眼. They all have the Chinese name. And they work in all kinds of wavelengths to collect as much light as possible. And here I also list some of the space missions under construction or scheduled in the next 5 to 10 years. Please keep an eye on this kind of big news that will bring out in the next 5 to 10 years. Okay, so that is TOO, the telescope for the observers. What about for the theorists? In fact, every astronomer is multifunctional. Theoretic physics, they stare at the blackboard, do calculations, and make predictions. Astronomers build equipment, design observations, and analysis of data. This is modern astrophysics. We also mentioned about the big question in astronomy, that is, where do we come from? So we're bringing astrochemistry, and are we alone in the universe? And we're bringing astrobiology to simulate the extraterrestrial environment and to understand how do matter cycle and store. The lab is really a necessary thing. And high-speed computer also plays an essential role, not only in reducing and analyzing the data, but also in generating and testing the theoretical model of astronomical objects. Even when we completely understand the underlying physics laws that govern the behavior of the particular object, like two-body collision things, often the object is so complex that it would be impossible for us to use our pen and paper to calculate their properties and behavior. Well, so we need the assistance of the high-speed computers to run like the N-body simulation, the Millennium simulation, and so on. And we cannot separate the physics from astronomy. I spent a weekend in summarizing all the Nobel Prize in astronomy and astrophysics. And from this kind of list, we can find that, especially in the 20th century, the beginning of astronomy, there are some greatest theoretic physics predictions, and they are proved to be true in astronomy observations. and also astronomic phenomenon. In most of the time, they challenged the established physical sketch of the universe. So to understand them also promote the physics understanding of the world. When the time enters the 21st century, the universe is the biggest physical and the chemical laboratory. That's our point of view. So from this century on, people discuss more about the extreme conditions the universe it has. So in this super dense, super hot, with high pressure, high magnetic field, high radiation environment universe, we detect the neutrinos, cosmic microwave background radiation, the gravitational wave, and we proved that our universe is expanding, and we're looking for some future to probe as much universe as possible. Okay, so as I mentioned, the communication is an essential skill. In 1972, the Pioneer number 10 spacecraft, the first human artifact that leaves the solar system, was launched towards Jupiter. With it, we attached our first message, a plaque carrying a greeting to any civilization that might find it. It shows a naked man and a woman next to the silhouette of the Pioneer spacecraft. And the top of the drawing shows the spin transition of the hydrogen atom, and the bottom shows the trajectory of the spacecraft within the solar system. The radial pattern represents the position of the solar system within the Milky Way by triangulation among a set of 14 pulsars. At that time, when it was launched, there are a lot of social debating. So many complained about the nudity, and the feminists objected to the fact that the man who is raising his hands in greeting, but the woman didn't. Also, some people found the pulsar map to be obscure, wondering how aliens would decipher it if they could not. However, this plaque illustrated our first difficulties in trying to encapsulate the essential of the human beings in a very short, concise message. And then 5 years later, in 1977, the Voyager spacecraft was about to launch. So instead of the plaque, this time there was a golden record that was attached to the spacecraft. Both images and the sounds were encoded into the record, and instructions were etched on the cover as well. I'm not sure if the aliens can read the instructions or not, but in an attempt to present the diversity of the humans and the nature environment, well, a wide variety of images were included in the record. At this time, there's no nudity, but with all kinds of the sound. The natural sound selected from whales, rain, and footsteps, and of course a kiss. And the music such as Bach, jazz, and rock and roll, but also much long Western music. Well, the spoken greetings in 55 different languages. Although they have a lot of effects, it is difficult not to see the record as a message to us as well, rather than an alien civilization. So one day, if you're like walking near the beach, if you catch such kind of records, how can we explain it? Even we cannot decipher them. But that's the effect we can make. It's our message in a bottle. We're toasting, hopefully, into the void of the space. Well, rather than the creation of the technology to launch something that can accelerate the speed of the light, why not we just stay here and receive some natural message? Well, the electromagnetic wave are the preferred carriers of the information, and they are easy to transmit, modulate, and receive. The radio waves contain the least amount of energy per photon, and so are the most efficient to reproduce. They are not easily absorbed or scattering by the gas and the dust in the interstellar medium, like the higher energy waves. The frequency range where naturally occurring cosmic noise is low. providing us a quiet zone to receive the message. That's our ideal thing. Well, although we have already been listening and sending messages for years, unfortunately, we got nothing. Or we may get something, but we don't know. What is the best way to communication? And we still haven't figured out. But for us, as the students, of course, the coffee break and the retreat, they're definitely the most efficient way of communication. And the last topic I'm going to cover in 5 minutes, that is, what kind of astronomy training can Xiamen University offer you? Well, let's talk about the situation nowadays, especially in the mainland of China. I was studying in the mainland of China from my undergraduate to graduate school, and I moved to Europe, to the US and Japan. Yeah, I travel a lot. And well, according to the statistic, the beginning of this year, the observatories nowadays in China are at some places, including Beijing, Shanghai, Nanjing, Yunnan, Xinjiang, and those observatories belongs to Chinese Academy of Science. And this table also lists the 16 universities in China which have departments of astronomy, and they are ordered by the year of the foundation. Well, Xiamen University, it's nice to have both the main campus and the Malaysia campus. So it is a good news that Xiamen University has its physics department, and the students are really willing to learn something about the astronomy. And if you still have your curiosity and the passion, you can just keep on going or pursuing your dream to apply for the graduate school or further education. But learning some astronomy 101 course, I'm currently trying to do some advertisements for my lecture course. And that is quite, I think it's quite important, no matter you are doing natural science or literature. You may need to know something about the scientific methods, how we think scientifically, and how we know our universe in a scientific methods. And then you may notice that the department of Xiamen University was written as found in 2012. In fact, it has a much longer history. Well, this is a professor Yu Qingsong, and he found the astronomy department in September 1927 after he got his Ph.D. degree from the Lick Observatory in the US in 1926. But unfortunately, 3 years later, this astronomy department was closed, and unfortunately, because of the lack of the historical material, we still don't know the reason. But we know that is Professor Yu Qingsong moved to Nanjing, and he found Purple Mountain Observatory in 1929, and also Fenghuangshan Observatory in 1938, and this Fenghuang Mountain Observatory that is now Yunnan Observatory. And here are all the professors and the associate professors, and with their profiles, you can check in the link I gave to you. That is the astronomy department link. I write it down. And also, our department is a kind of medium-sized department, but we have all the professors in different fields. We're doing this multi-wavelength observation, theory, simulation, and we also have close collaboration with some Purple Mountain Observatory, Shanghai Observatory, and the Beijing Observatory. With those instrument engineers, we have a lot of observation and the theoretic programs get involved. So if you're interested, you can find these professors, and if you have any question, you can ask them, or if you want to work with them, please write an email. They're all very nice. And so that's about the end of my public talk, and I hope you can understand probably 70% of it. And here I also attach another video. It's about 5 minutes. And that is from a friend of mine who was instrument engineer working in Mauna Kea for Gemini Observatory. But after he got his PhD degree, he decided to move back to the mainland of the US in California, and he got a job working for NASA. And he was a very excellent instrument engineer and a great photographer during his leisure time because he lived in Mauna Kea. That is a heaven for observation. He got a chance to watch the night sky and taking a lot of time-lapse videos and pictures, and he won a lot of photographing like tournaments or prize. Even he was, those pictures are like on the National Geography cover pictures. And this time lapse, that is for 5 minutes. And I asked his permission to download from his personal homepage. And let's enjoy. And after this video, I'm happy to take any questions. Okay, so that's my public talk, and I'm happy to take any questions. Probably I will have to stop sharing, and yeah, or I'll just leave this window open and to zoom it a little bit larger in case you have any questions.
Okay. Yeah. Thank you very much, Dr. Feng, for the talk. It was very interesting. So, yeah. So let me open to the audience. Does anyone have any question? You can unmute the mic and ask us the question. For some of us, you can type in the chat. I don't know. I think not everyone can type in the chat. So, but you can certainly ask questions through the microphone. If there's anyone have any questions. I have quite a few, but I will let the audience ask some first.
Yeah, usually my students, I've already noticed some of them are showing here. They usually like typing when I was giving the lecture. I was sort of a to check that. And usually when I do this lectures, I do the pre-recording, and when I giving the lectures, I play the video and answer their questions by typing or by speaking.
Oh, that's interesting. Okay.
Yeah.
I'll ask my question first. Like because well, I have a question about the video that you just shown also. So, like because I'm not familiar with observational kinds of things, but in the video there's always those I assume there are laser lights shining out of the telescopes to track the things, right? So yeah, can you explain more? Like, what is it for the human eye to guide the human eye, or was it some other instrumentation to work with some other things? Like, how do they work basically?
That is a very interesting question, and I just gave this lecture about the adaptive optics. Last month, usually there's some turbulence in the atmosphere, and we get the image. We don't know how the turbulence that is, so the image we got is blurring and it's vibrating, right? So we need to find a reference to guide the star, and usually we have some different types. If there is a star, bright star nearby, the star, it moves, but it didn't move rapidly, right? We take them as a kind of the stadium star, and if there is a bright star nearby, we take them as a reference and correct such kind of turbulence because of the atmosphere. But sometimes if there is no bright star nearby, we make the artificial laser pointing to the sky near our observational object. So if there is a turbulence, the laser jet will turbulence, and we use it to correct it. That is adaptive optics.
Oh, okay. Wow.
Yeah.
That's interesting.
And different laser jets from sodium and from the excitation of some other atoms, they're used for this guiding at different altitude.
So the lasers are visible in the optical range.
Yeah, yeah.
That means for a person walking nearby, they will see that laser shining out of the thing.
But to the telescope, because the lasers have very high energy, don't point it to your eye. And this guiding system is for the optical observation. For the radio observation, we don't have this kind of laser jets. And optical and the infrared observation on the grounds, they use such kind of thing.
Oh, okay, I see. Yeah, anyone else? So my other question I wanted to ask was about the observation time, because you said observation time is actually like you need to share with other people, right? And then you also mentioned weather is a problem. So if on that day the weather is bad, then what happened? Is it wasted, or is that some way to make up for, to compensate somehow? Or will it be a very frustrating day for you if the weather is bad?
Yeah, I happen to come with such problem quite often, and sometimes if the yeah, it's just like I was so misfortunate, and the weather that has less effect on the radio band than the optical band. The optic band they can only observe at night, and we can, the radio astronomers, we can run our observation all the day. But sometimes the water vapor is too high, so we cannot get the very weak signal, or if there is raining, or if the wind speed is too large, we cannot predict them, so we have to stop our observations. And usually if we want to get our data, the first step is we check the archive, but not everybody are interested in that particular source. So some of them are not have the archive data, or their observation, they don't have enough sufficient sensitivity to reach your scientific goal. So we have to prepare and proposal for getting the observation time. But as you know that there are a lot of people, and the pool is very small. There are a lot of fish. So not all the fish can eat all the meals. So we have to compete with some other observers to get the time.
Okay, I see. Thank you. Thank you. Yeah, I guess this is something that usually students haven't thought about, right? Like the preparation of the observation is also important.
It's sometimes frustrated, but sometimes it's fun, because for the radio astronomers, we usually go there to do the observation by ourselves. And those observatories, they all in the very cool and beautiful place. So sometimes if there is a rain or snowstorm, like what I show in this picture, yeah, there's heavy snowstorm. I've got like 7 nights granted, but there are half of the nights we have snowstorm, so we cannot do the observation. And our radio telescope, it's just like the big antenna. It's just like the hotspot. And if it do the observation during the snow nights, it's just like the full dish will be covered with the snow, so we cannot get high quality data, and we have to wait. And for some of the telescope, they have the heating system. So the next day we can run our observation if that is sunny and clear. But for this observatory, yeah, they spend another day in melting the snow, so I cannot do anything.
Wow. Okay. That's
That time,
interesting.
that is a chance we go skiing.
Oh, okay. Nice, nice. Oh yeah, by the way, I should mention the audience can also ask questions in Chinese.
Oh,
if if anyone wishes, yeah.
冯老师，那我问一个问题哈，您刚才介绍的都是一些大型的观测计划或者是一些大型的仪器，我想问一下，因为现在下面有一些学生，他有一些社团啊，他有一些简单的仪器，如果他们要做的话，除了拍一些照片的话，你觉得他们可以观测一些什么东西，然后能够对科学有帮助的吗？
Oh, since you're asking me this question in Chinese, I'll answer you in Chinese as well. So sorry for those audience who speak English. 一般来说，在各个高校，特别是像厦门大学本部，我们有一些早期的本科生，就是对 undergraduate student 早期科研训练，他们基本上是在大1、大2的时候可以去联系，像我刚刚就是秀照片的这些所有的 faculty member，他们有他们的 specialized，他们也有一些 topic， 就比如说像我自己的 topic 有特别多的数据，我非常愿意去就是带这些学生入门啊，告诉他们有一些天文的软件怎么使用，怎么去处理数据什么的，所以他们可以如果感兴趣的话，可以翻这些老师的主页，然后联系他们，并且问问他们是不是有这种暑期实习啊、training 啊，或者是早期科研的机会。这样子的话是也就不仅仅是拍照片，仅仅拍照片的话是属于天文社团他们的一些工作。
好，谢谢。
Oh, there's a message.
Let me just check that.
If you can't see, I'll read it to you. So Professor Wang Huixiong says, hi, Dr. Feng. Thanks for the great talk. In some case, there is the need for radio telescope from different places, even different countries, to collaborate with each other. For example, the capture of the black hole photo, I guess the EHT. So could you please explain how different telescopes work together?
So let me just use two steps to answer your question. So first, you know that the different telescopes, they work at different wavelengths. As I mentioned, there are different transmission window. The atmosphere of the Earth is kind of like blocking system. They blocked most of the wave bands from the infrared, far infrared to the high energy. That is gamma ray, like X-ray, something like that. And the only narrow window that we can run the observation is the radio band, and like the EHT telescope. So there are two cases. Usually, if we use different telescopes at different wavelengths, we collect information at different wavelengths. And as I mentioned to my students, we usually have the Veillon's law, and that is a radiation, like the black body radiation. And they cover the different wavelengths. To collect the different wavelengths, we can collect the luminosity of the object and study just like the color index, spectral index. And we also check upon the chemical compositions, like there are different, if you know the spectroscopy, there are different vibration, rotation, and molecular lines or atomic lines. So that's why we use a telescope at different wavelengths. And the EHT, you mentioned that there's a telescope working at the radio wavelengths, especially the millimeter and the sub-millimeter. That is another capability we judge whether the telescope is good or not. The telescope, they have two capability. One is they're going to collect as much light as possible. So we make a larger telescope, and that is called the aperture. And the second capability, that is angular resolution. We're going to see as small as possible of the object or the far object. You know, the black hole, we cannot see the center of it. We can only observe the horizon of the black hole. But with one telescope, you know that in the physics, there is an error. It's a dilution limit, and that is the angular resolution is equal to lambda, that is a wavelength, divided by d, the diameter. As I mentioned, the larger the diameter is and the smaller the wavelength is, the smaller angular resolution you will get. But even with this larger diameter, the radio wavelength, it has a very long wavelength. We still got, like, the best single dish telescope got 10 arc seconds of the angular resolution. That is not enough to resolve the black hole. Even to the horizon, we cannot resolve that. So we make the diameter of the entire Earth. That is called the baseline. We make the baseline as long as the entire crossing the Earth. Well, later we are going to make the baseline towards to the moon to make a even longer baseline. In that case, we can reach a smaller angular resolution to resolve as small object as possible. And this small object, they can correspond in the small structure, like 0.1 arc second structure, or even higher structure, or to the very distant object, because the angular resolution, and there is a relation with the distance. The higher angular resolution, you can observe, the further distance you can reach to see that kind of object. So that is the reason we need the collaboration for the telescope at different place and working at different wavelengths.
Okay, thank you very much, Dr. Feng.
Thank you.
Oh, speaking of these methods, right? We have the technology to take the picture of the black hole already. Can we do something similar to take pictures of, let's say, exoplanets or some other objects?
In principle, we can, but the extraplanet we have the problem is, well, the optical telescope, they take the picture of the exoplanets because their wavelength is quite short, and the larger aperture of the optical telescope. Nowadays, the big optical telescope, they can reach more than 8 meters and 10 meters large. They can like resolve those things, but the exoplanet, they don't radiate light, and they just reflect the light. So their signal are quite weak. And usually we can only detect the signal of the exoplanet by different methods. For example, the transition, and also the eclipse of the exoplanet in front of a star or something. But currently, we are not able to take in picture. And if we extend its baseline to make 2 different antennas at different place of the Earth, to make the Earth as a baseline, that is possible. But the interferometric technology for the optical telescope, that is tricky.
Oh.
We use this technology for the radio telescope, and that is well established. And people have already have some idea or proposal to build such kind of optical interferometer, especially for the VLT in Chile. And let's wait for 5 or 10 years to see if they can catch that or not.
Okay. Okay, thank you. Okay, so does anyone else have any questions?
Yeah, both Chinese and English.
Yeah, both Chinese. Even in Malay, I can translate.
Oh, okay. I thought you don't speak Chinese.
No, Malay. I don't speak Chinese, but I can speak some basic words only. Okay, so I think if there's no other question, we can thank Dr. Feng. So wait,
can I ask a question for Dr. Feng?
Yeah, Dr. Siti has a question.
Hi, Dr. Feng. Thank you for your informative talk. Okay. Since this course is being offered to this astronomy course is being offered to the physics students, and also there's a astronomy in Xiamen. So I would like to ask you about the final year project for the student. Normally, what kind of final year project being offered or suggested to the final year student?
You mean what kind of student?
What kind of astronomical related final year project being offered to the final year student?
Like the thesis at the end of the undergraduate?
Yeah, for the thesis at the end of the semesters.
Okay. I'm not sure about the policy for the Malaysian campus, but I suppose, well, usually I can tell the situation here in the main campus. Usually, as students, they can ask for this professors for the final year project. And sometimes I know that there are some good students in the main campus of Xiamen University. Their final project, they're really a thing. They published paper in Astro PH letter. So I'm not sure if the students in Malaysia campus also have this chance, but I suppose we can talk with the department to see if that is a possibility or not. We can have some conjunct or projects.
Okay, so normally what kind of project involved? I mean, is it like observing or yeah?
So I can tell you the situation for the main campus. Usually from the second year on, the students can ask if this professor they can follow with and study something about the specific fields, as I listed all these fields, and you can find their names on their website for their specialty, and you usually write an email to them or talk with them face to face to check with them. Usually for my students, I talk with them and ask what is your interest, and it's just like double side. And then after I know what that person is interested in, I will list different projects I have and open and let that person to pick. And of course, there are a lot of like things for the self-motivated students. Usually I cannot do the hand-in-hand thing, but I teach you. It's just like all these professors, including me, we're the instructor, will teach you how to do the astronomic research. And the goal is we can at least write a scientific paper, no matter if that can be published on those astronomic journal or not. But those papers, either they will stop journals, or if they are good enough, we recommend those projects as published to SPH or something else.
Okay, thank you so much for the explanation. That's great. Yeah, that will be a good opportunity for the student to do the final year project. Yeah.
Yeah, but it's better that you can start to contact with the professor from second or the third, because usually the project that takes time, or at least for the observation project. For example, for me, I'm a radio astronomer. I don't expect the undergraduate students to present a proposal and started to do everything from the scratch, like presenting proposal, do the observation. That usually takes about more than 3 years. That is for the graduate students project. But for the undergraduate students, I will ask them to read some background papers, know the current status and the problem of this field, and then I will give them some data, try to run codes, do the data reduction or the analysis by themselves. Usually, if they have questions, they can come to me and we can discuss. For some of the, because for the astronomy, it's a kind of like exploration. We cannot predict the results before we start, right? So I work with some undergraduate students. Sometimes the results are beyond my expectation, and that is good. So better to prepare as early as possible. Is that answering?
Yeah. Thank you so much.
Okay, let's see the chat. Let me double check. Okay, so I think if does anyone have any question? I don't know if I'm hearing some sounds. Wait, let me see.
And for all the things I talk in my slide today, because that is for the public outreach, and my students, you know that some of the slides are from my lecture, and I really want you to be my students and we can learn together, because teaching, especially for the astronomy 101 course, it's a kind of like refresh my memory. I took this kind of course like 15 years ago. So that brings me a lot of new knowledge when I prepare for my lecture. And if you have the chance, I'm not sure if the students from the other departments can select this kind of astronomy 101 course or not, but I will try to discuss with the department if they will got this or not.
Okay, yeah, that would be great. We do have a general education, but yeah, definitely it will be see how the department, how everything works out.
Okay.
Yeah, okay, so I think let us thank Dr. Feng. So we are all online, so it's hard to give an applause, but you should give a round of applause for Dr. Feng for a very excellent talk. I've learned a lot of new things from this talk as well. So
The thing
yeah.
I usually talk with my students, the communication, that is the #1 thing in astronomic research.
Yes, I agree. Yeah, that's true. Okay, so yeah, thank you everyone. Thank you, Dr. Feng, and I think that's all for today, I guess. So wish everyone have a nice day, and thank you all for coming. And thanks again, Dr. Feng, for the talk.
Bye-bye.
Thank you. Bye. Take care.
Okay. Bye-bye, everyone. Take care.